Hello, welcome to the webinar. We'll wait just a minute or so to let everyone get logged in and then we'll start. Okay, I think we're ready to start. Thank you for joining us today. I'm Jessica Finnegan with Nullspace. Welcome to part one of our three-part webinar series. Today will be an overview of Fortify's 3D printing process and Nullspace's EM simulation software. Today, we're excited to hear from two experts in their relative fields. First, we'll hear from Phil Lambert, Head of Application Engineering at Fortify, and then we'll get to hear from Dr. Daniel Faircloth, who is the CTO of Nullspace. At the end of the presentation, Phil and Daniel will have the opportunity to answer questions as time allows. Please put your questions as they come up during the presentation into the Q&A or into the chat, and we will address those at the end. And with that, I'll turn the time over to Phil.
All right. Good afternoon, everybody, or good morning, depending on what time zone you're in. I'm pleased to be here today with Nullspace and Daniel and Jessica and Masha and everybody involved, and we're excited for this webinar series. And to get started today, I am going to briefly introduce Fortify, talk about some of the aspects of our technology and where we apply it, and then walk through a few applications at the end, and then hand it over to Daniel to do the same for Nullspace. So to get started here, I just want to talk about Fortify for a second. Fortify offers full stack design to manufacturing services for RF devices. On the front end of that workflow is RF design. We offer design services through our experienced team of RF and applications engineers, both on the RF side and the mechanical engineering side. And we work with your designers to optimize your antenna design. We also work with a variety of partners, including Nullspace and Iris on the design side as well, depending on the application and depending on the antenna and the complexity of the problem. Fortify also offers prototyping and testing services that enable our customers to have fast design iteration loops for their prototype or for their product development lifecycle. So we do that here in our labs at Fortify in Boston, Massachusetts. We also have a network of certified and qualified manufacturing partners when that device has been developed to the point of scaling manufacturing. Our partners are located domestically in Connecticut with TTM and internationally in Switzerland with Varioprint. And through those partners, we're able to offer scale manufacturing to our customers. Next slide, Daniel, please. And so Fortify offers these capabilities to a variety of markets, including the ones listed here. On the left, we have satellite communications. Our customers are using our technologies for different types of antenna systems for simultaneous multi-beam, multi-band communications. We've also explored tactical communications market for some of our customers, including 5G on-the-move comms for ground systems and UAVs, and also mobile command posts using some of our lens antenna applications. We're also working in the signal intelligence market and surveillance market. In that market, some of our customers are exploring our technology and using our technology for high-gain radar with increased field of view. And they're also doing work in tracking and guidance, where our customers are leveraging our technology for high-performance, low-cost airborne guidance systems. All in all, our customers in Fortify have been using this technology for high-gain, enhanced field of view, and enhanced swap-C systems. So moving on. And so these components that we make are to solve a variety of limitations in specifically beam steering antennas. Beam steering antennas tend to have limited field of view. They tend to have limited bandwidth, have high power consumption and high costs, especially if you're thinking about phased arrays or AESAs. And Fortify uses a concept called GRIN lensing to resolve many of these beam steering antenna limitations. Our antenna lenses offer extreme field of view, up to plus or minus 90 degrees field of view, offer extreme instantaneous bandwidth. We're working on lenses right now that have been measured to have 3 to 40 gigahertz of instantaneous bandwidth. And these lenses have been introduced into systems that have a reduced power consumption compared to the competitive technology. and lower cost to manufacture those competitive technologies and lower cost to operate. And so I made a reference there just a minute ago to GRIN lenses. And so what are GRIN lenses? If we move forward one slide, Daniel. GRIN is an acronym that stands for Gradient Refractive Index lensing. So that's what GRIN stands for. And Fortify offers the design and manufacturing services for antenna systems using this GRIN lensing technology. So on the left here, in the left diagram, there's a dielectric constant on the y-axis and radius on the x-axis. This is a dielectric profile for a Lundberg lens. And so you see it goes from about 2 at the core and to about 1 dielectric constant at the surface. And we accomplish this type of design where the gradient transitions gradually, the dielectric constant transitions gradually across the volume of a lens. And we do that by using latticing geometry. And so on the rightmost image, you see the cross-section of a lens that is entirely designed to be a lattice. And what we're doing is locally controlling the volume fraction of air to dielectric material. And by locally controlling that ratio of air to dielectric material, we're able to create an effective media where we're locally controlling the effective dielectric constant by varying that volume fraction of material. And so the lower density areas where more concentrations of air have lower dielectric constants. And then towards the middle here, where things get a lot denser, have a much higher dielectric constant. And so by leveraging this type of technology and using a 3D printing process, we're able to create true gradients of effective media, of effective dielectric constant, to realize these gradient refractive index lenses. All right. And this isn't essentially a new concept. In fact, a gentleman named Lundberg, go figure, first ideated the Lundberg lens back in the 40s. But for years, there hasn't been a real manufacturing technology that folks have been able to leverage to actually manufacture these lenses. Since the advent of 3D printing, there's been quite a bit of investment in the academic side of gradient refractive index lensing, primarily around these technologies I have on this chart here. At the top, we have filament extrusion, sometimes called FDM, fused deposition modeling. And this is probably what you think of when you think of 3D printing, where there's a little nozzle and the nozzle is extruding thermoplastic material. And these machines can have great resolution. They can have great resolution to make these gradient refractive index lenses because it is primarily primarily defined by the size of the nozzle through which you're extruding your material. And they have great dielectrics, right? Things like ABS, polycarbonate, Ultem. These are things that folks have used to create lenses in the past. However, you're primarily limited here by throughput. If you want really high resolution, your nozzle has to be really small, which means you can't print a lot or you can't print very quickly. And so folks have started, especially in the academic space, have started to look at other types of technologies to make lenses, including polymer jetting. Polymer jetting is another type of 3D printing process where you jet thermoset materials, photo curing materials through a really tiny array of nozzles. These nozzles are super small, the droplets are super small, which means you also have great resolution. And there are also throughput benefits here. However, thermoplastics have great dielectrics, where thermosets historically, especially the ones that are 3D printable, or the photo curing ones, have historically not had great dielectric characteristics. Same story for vat photopolymerization. You might also be familiar with this technology. Stereolithography or DLP both fall into this category. Great resolution, great throughput, but also quite limited for the same reasons in the dielectric performance of those materials. DLP does have significant throughput advantages because you are exposing entire cross sections of a layer at a time. But again, historically limited in the material properties. That's where Fortify comes into the market. We offer the resolution, the throughput of DLP, while also offering great dielectric materials to create these gradient refractive index devices. You can move on, Daniel. And we do this on the back of a digital light processing 3D printer that we developed in-house at Fortify. So this is a type of 3D printer that's bottom-up DLP, which means that the light engine is exposing UV light from the bottom into the vat of photopolymer resin. The build volume is about the size of a shoebox, the common shoebox, 8 by 4.5 by 13 inches. And we typically print with a 3D pixel called a voxel of about 75 microns. So you can think of a little cube that's about 75 microns being the fundamental resolution of our printing technology. And we use this 3D printer to make all of our lensing products. And we do that with the materials that I'm going to show you on the following page. So Fortify offers 3 excellent dielectric materials right now. Starting at the bottom, this is Radix 2.8. This was developed in collaboration with Rogers Corporation, one of the first high-performance, high-frequency, low-loss printable dielectrics in the market. The dielectric constant of 2.8 and a dissipation factor of 0043. Those data points are from measured at 10 gigahertz, 0046 at 24 gigahertz. Now, that's a great material to use for Lundberg lenses because the effective permittivity range that you can achieve with that lens, with that material, is somewhere between 1.2 to about 2.3. So it's really great for that Lundberg dielectric distribution from 2 to 1. Now, if you need a little bit more flexibility in your design and you need a higher dielectric constant range, we also offer the Rogers Radix 4.6 material. This is an emerging material, and it has a base dielectric constant of 4.6 and a loss of 0040, very competitive in loss with the Radix 2.8 material. What's interesting here is that we're able to use that same latticing technology, but achieve a much broader range of effective permittivities. So somewhere from about 1.6 up to about 4, depending on what frequency range you're trying to operate in. And so you can't get as low as a 2.8, but you also can get much higher. Now, if neither of those meet the needs of the antenna lens that you're trying to design, we also have Radix. We also have the aluminum material that we developed internally called Alumina 97. Is a dielectric constant of around 8. And this is a sintered material, which means that you 3D print the green body. You take that green body into a sintering oven, and you sinter that up at 1600 C. That material, when sintered, has a dissipation factor of 0002, so very low loss sintered alumina ceramic material. These are all options available for designing your lensing. All right, next slide, please. And Fortify does our lens design through this RF-specific digital workflow. On the front end of this workflow is EM simulation with groups like Nullspace, where they're doing the design and simulation to create and determine what the perfect dielectric constant distribution is. That distribution, that RF dielectric distribution and volume which you're trying to populate with that distribution is then interpreted by Fortify to create that lattice geometry that results in that effective permittivity I was describing earlier. And Fortify takes that design and brings it through our build generation tool sets to support that part for 3D printing, to slice that part, and then ultimately 3D print it. So you can see on the bottom left there, we have 3 lenses on the build plate with the support structures. After those parts have been post-processed and final cured, and in the case of the ceramic materials, sintered, we can assemble those with our active antenna components and bring it into a range for antenna testing to get those test results. And then we can repeat this process very quickly through the powerful tools in Nullspace and the rapid prototyping capability of our technology at Fortify. Next slide, please. And all of this is being leveraged across a variety of markets, including A&D and commercial markets for step change performance. And as I was mentioning earlier, our customers are using these lenses to introduce increased efficiency, increased bandwidth in their antenna systems, higher directivity, especially in wideband systems like a quad ridge horn, where you have a lower gain at the high end of your performance curve, and you want to introduce some gain enhancement at the high end there. You can do that with our lensing. Wider field of view, which I'll talk about a little bit more detail in an upcoming slide. And then similarly, reduce scan loss, where you may not necessarily be looking for a wider field of view, but instead maintaining your field of view and reducing your scan loss component. And then, of course, introducing lower cost here. So this technology is low labor manufacturing. And when you're introducing these types of lenses into your systems, there are benefits that you can take advantage of, such as reducing the number of chips in your phased array system, or reducing the number of towers that you need to cover a sector. And I'll show you in a couple slides here how these lenses can achieve these types of benefits. All right, just walking through just a few applications here. looking good on time. So the first one I want to talk about is a field of view enhancing lens. And so these lenses enable you to have complete coverage over a sector, say in a commercial fixed wireless access application, with fewer antennas. And so typically these phased array antennas deployed for millimeter wave 5G might have a sector that covers 120 degrees. So that would be plus or minus 60 from foresight. So plus or minus 60 degrees from foresight. In order to cover all those sectors, you probably need 3 or 4 antennas. And so, sorry, in order to cover a 360-degree sector, 360-degree coverage, you'd probably need 3 to 4 antennas, each covering 3 or 4 sectors. Now, with our field of view enhancing lens, which is an optimized lens that sits on top of your phased array unit, you can take that 60-degree beam and turn it out to 90 degrees. And the only real compromise you have here is the depth of your antenna. You're no longer a flat panel array. You're going to have slight Z depth to it, so you have aperture out at 90 degrees, so you can create that beam and read and signal from that direction as well. And so what this allows you to do is reduce the number of systems you need to deploy, which helps to reduce your CapEx costs and your operating costs for the same type of coverage. If you look at the little graphic at the bottom right here, you can see the dotted red line is a reference scan loss factor of 1.2, which is pretty typical for many phased array antennas. And then for this specific demonstrator that we created here, sits on top of an Anoki wave development kit. That dotted black line on that same chart is the data from that specific antenna without the lens on top of it. And you can see that out to 80 and 90 degrees here with the field of view enhancing lens, we're able to create beams 3 dB down from foresight out to 85 with signal out to 90. So this is one really compelling demonstrator that we've created to show off the capabilities of some of the higher dielectric constant materials for grid lensing. I got one more example to show you here, specifically for satellite communications. For low power, low complexity, wideband SATCOM aperture. So what you're looking at here in the center is an image of a gradient refractive index lens that is 13 inches in diameter, so assembled from 6 discrete 3D printed components that we glued together. And this is part of a type of antenna architecture called a switched beam lens antenna. And so these switched beam lens antennas are very wideband, very low power consumption, and relatively very low cost compared to the alternative to solve this type of problem, which would be phased arrays. And so for those of you who are familiar with phased arrays or AESAs, they are very complex, very power hungry, and quite expensive, and quite narrowband typically, and primarily limited by the phase shifting, the bandwidth of the phase shifting elements. And because those phase shifters are each tied to because we're using those phase shifters, and there's a lot of them depending on the size of your antenna array and how many elements there are, that tends to drive up costs and significantly reduce the bandwidth of that antenna system. And if you switched instead, or if you didn't need the resolution of a phased array antenna, and you could the pointing resolution of a phased array antenna, and you could instead use discrete beam positions with perhaps maybe a 3 dB down overlap between your beams, you could switch to a much lower cost switched beam lens antenna architecture, where you have a switch network connecting to an LNA and an antenna element. And depending on where that antenna element sits behind your lens, you can create a beam that points out at a fixed position. And all of the phasing, instead of happening in those phase shifters, is happening in the lens, and the lens is true time delay, which means that the lens itself is very wideband. So you are at this point only limited in your bandwidth by your antenna element and the electronic components in the back end. There is a upper bandwidth limit that's driven by the unit cell size, which I'll go into in more detail in the upcoming webinars. But because the lens itself is true time delay, we're able to see very wide instantaneous bandwidth for these satellite communications, enabling the capability to do LEO, GEO, and MEO SATCOM simultaneously just through one aperture. So super compelling, reducing the number of apertures you need to deploy, providing that you can tolerate that slightly reduced resolution your beam positioning. All right, that's it for the application exposés in this webinar. I'll go through many more in the following episodes of this webinar series. But the last item I wanted to touch on here is this patch-fed grid lens. And this patch-fed grid lens is a lens that Daniel and I have been working on. And it's designed with very low viswar and very small size, but to be competitive in gain with a standard horn antenna. And this is a great test vehicle. And we've been using this to demonstrate this entire workflow from RF simulation to manufacturing to test. And we want to use this as the through line throughout the series of webinar episodes, so that you can follow everything that we do in these workflows through this one example set. So now I want to pass it off to Daniel, who's going to take over the presentation and talk about Nullspace and their simulation capabilities. Looking forward to questions at the end. Thank you very much.
All right, thanks. So, as Phil mentioned, this concept of gradient index lenses provides some really nice design flexibility that historically has not been available until companies like Fortify have been able to create the fabrication technology necessary to yield them in the real world. And so necessarily that raises the question of, well, if I have all of this fabrication flexibility, I need the design tools to pair up with that. And that's where Nullspace comes in. So I'll give a little introduction to Nullspace, the company, and our products, and then touch on some of the design workflow associated with lenses and specifically this cylindrical grid lens, which will be, as Phil mentioned, a thread running throughout the series of 3 webinars. So Nullspace is a relatively new company. We spun out from Iris Technologies, an established defense contractor, about a year ago. And Iris, being an electromagnetics technology company, they recognized the need for a solution to enable the engineers at Iris to develop next generation RF technologies more effectively. And really the key to being able to develop these new technologies is rooted in fast and efficient and accurate simulation tools. And that software technology was found to be lacking. So about 12 years ago, what is now Nullspace began to be developed, and those software technologies were matured and validated across real world applications over those 12 years. And then last year, Iris spun out as an independent company to offer our technologies to the world. So one of the first questions that people often ask when presented with a new simulation technology is, how do I know it works? You know, if I'm going to integrate this new simulation technology into my design workflow, in some sense, I'm taking on a lot of risk. You know, that this tool that is critical to creating new designs is going to be accurate and trustworthy. And so, how do I know that this tool will meet my needs and is worth the cost of learning to use it and to adopt it corporately? And at Iris, over the past 12 years, all through the course of the development of the technology that goes into Nullspace, it was being tested and validated on real world applications for Iris and its customers. You know, these technologies ranged in complexity and scale. For example, down here in the lower left, this image represents paint embedded antennas that Iris developed. So there's a voice comm antenna embedded into the paint applique on the roof of this car. The idea being, if I can get the antenna out of the windstream, it lowers the drag on the vehicle, improving fuel efficiency. It also opens up unobstructed space for better advertising. And so this was a very technologically challenging application. The antenna had to be very thin. It had to function over carbon fiber ground plane. and we had to ensure that the antenna pattern, when simulated on the full vehicle, could achieve the link budget necessary and was worth the change to swap out the traditional monopoles. There are a variety of other applications here. This is a large scale phased array used as a radar for lower tier air and missile defense. It's an extremely electrically large, electrically complex example. And our customer at the time for IRIS had a challenge in simulating this full array and had some very specific performance questions associated with that. And only through the capabilities of Nullspace was IRIS able to answer that and provide those answers with confidence. And then, of course, as we've been talking about throughout the webinar, being able to simulate additively manufactured lenses like these Lindbergh lenses here. IRIS develops polyrod antennas, which are wideband, high gain, low cross-sectional area antennas. And these are products that IRIS is developing using Nullspace technology in conjunction with Fortify's unique printing capabilities. So that just gives you a highlight, a wide variety of applications, a wide range of scales from electrically small to very electrically large problems that have been used to validate and verify the performance of Nullspace over the past more than a decade. So with Nullspace, we have two products, Nullspace Prep and Nullspace EM. And the workflow that you see is fairly typical of any kind of computational physics software package. You, as the user, begin with an idea or some customer requirements or an existing CAD model. You bring that CAD model or create a CAD model in Nullspace Prep that handles the geometry creation and manipulation, CAD cleanup, and preparation for simulation. You can create meshes in Prep, and then that meshed geometry flows into Nullspace EM, which is the computational kernel that produces the engineering data necessary to do any kind of post-processing for your specific application. And then through our Python API, you can visualize your results in any format that you like, whether it be radar cross-section, directivity, gain, VisWAR, return loss, what have you. All of that data is available. And running throughout our entire family of products is a very powerful Python API that allows you to parametrically and programmatically create geometries, automate the mesh creation, automate simulation processes, automate post-processing workflows, and provide that important feedback loop to support very complex parametric analyses, optimization, and uncertainty quantification. And if you've ever used the optimization capabilities in other commercial EM simulation software products, you've probably found it difficult sometimes to control the creation of geometry or control the processing of the data in a way that supports your workflow. And that's something that we at Nullspace have really focused on, enabling a very powerful and customizable workflow to support these next generation optimization capabilities. And going along with that, one of the primary motivations all along with developing Nullspace was striking the balance between speed and accuracy. A very fast simulation tool that gives poor accuracy results is not any good. And on the other extreme, a very accurate simulation tool that's very slow is also not very useful. So using some sophisticated technology that we've developed over the past decade, we are seeking to always maintain both. Have a highly accurate solution that is very fast and enables you to do more sophisticated, more complex designs than were previously available. And this is a very specific example highlighting that. This is an 11 by 11 array with dual feed patch antennas. So the idea behind the simulation is you want to synthesize the embedded element pattern for every one of the feeds involved in this array, and using that data then do weighted superposition of those patterns to yield a full array beam pattern. And then you can do optimization and beam weighting adjustment to study beam steering, and maybe get beam steering error or max gain roll off, and those important metrics in designing a phased array. Typically, this is a very computationally complex and costly simulation. Nevertheless, or never mind the fact that you may want to do an optimization, and then that involves multiple runs, and so it becomes an even more computationally taxing problem. And this is an example comparing a leading commercial software product that's available now versus the performance of Nullspace, running on identical hardware, running the identical geometry through the same workflow. And you can see with the leading commercial software tool, it took about 5 days to run the full simulation. And that simulation also took up about 700 gigabytes of storage on the computer that it was running on. With Nullspace, that simulation took about 6 hours, and post-processing was only about 15 minutes to produce a synthesized beam pattern. And all of the data necessary to do that only required 6 gigabytes of storage. So you can imagine, if the problem that you're working on occupies a full work week just to run the simulation, your appetite for performing parametric analysis or doing optimization is going to be minimal. You may not have schedule or budget to support that type of workflow. Whereas with a simulation that runs in 6 hours, now you can run multiple iterations per day, and by the end of the same time, from Monday through Friday, you've actually performed many iterations supporting a design trade. And this is going to open up the possibility of very critically identifying those design issues early on, supporting more sophisticated optimizations, even doing manufacturing uncertainty analysis, and just reducing the overall time to market to get your product out there. All right, so with that overview, let's look at how we address lens modeling with Nullspace Prep and EM. So there are a lot of different types of lenses. As Phil talked about, we were looking at some Lundberg lenses. There are other similarly analytically specifiable lenses like a Maxwell fisheye lens or an Eaton lens. And if you can specify that dielectric profile for your purposes, those lens types, using the array of materials that Fortify has available to its customers, you can design any of those types of lenses. However, looking ahead to more complex lens designs, all of those lenses, Lundberg, Maxwell fisheye, Eaton, and several others, are spherical-based geometries. And you may get into a situation where you don't have the volume to support a sphere geometry, or you want to try to reduce the swap of the lens in a certain way, or you want to optimize performance, and a sphere is not the ideal geometry to support that. So through Nullspace, with our flexible Python API, there are lots of different ways you can represent these lenses. I show two typical ways here on the screen. One way is through layers of different materials, and I show two spherical representations there, but obviously you could imagine planar layers or cylindrical layers, or really layers of any shape, if layers is the most optimal way of representing a gradient in the permittivity. Or you can switch to something even more geometrically flexible, such as voxels. And you can see there on the right, that's a voxelized representation of a Lumberg lens, where each voxel has a unique permittivity, as opposed to in the layered approach, where each layer has a unique permittivity. And so with that voxel approach, that's already geometrically very compatible with the unit cell based approach that Fortify has for specifying permittivities and how that maps into those lattice structures. And so you can create those, you can create the baseline voxel representation conformal to any geometry that suits your particular application, and then leverage Nullspace's accuracy and speed to optimize the idealized profile of that permittivity. So how is this done in practice? This is kind of an overview of the workflow to perform a lens design. So one of the most important things that we would start off with is, we select the maximum dimensions, the bounding box, the workspace, if you will, for how we're going to create that lens. Then, based on a number of factors, number of optimization variables, the overall shape, etc., you might choose either a layer-based approach or a voxel-based approach. And then based on that, you're selecting the number of layers or the voxel size, and that has to do with the highest frequency of interest that guides the selection of the number and thickness of those layers or the size of those voxels. Our API supports specification of a profile that then gets mapped onto those layers or voxels, or you can just say that this is an arbitrary structure. I don't want to presuppose any particular variation, and that's going to give you the most design freedom throughout the optimization process. Then, you would create the baseline model. So in the case of voxels, literally just a geometry of voxels. And we're going to sample the permittivity in each of those voxels, create a material library very specific to that selection. And then that goes into the design loop where we're now updating the materials in the model, performing a simulation, evaluating a fitness function, and then adjusting those parameters. So for example, if you were trying to do a field of view enhancing lens, you might be looking at peak gain roll-off versus angle as your fitness function, and then using the permittivity in the voxels as your design parameters. So using this general workflow, it's very flexible to support essentially any kind of EM optimization, whether it's antennas or scattering or microwave devices. You can use this basic approach with the Nullspace Python API to support your design. So, Phil showed that cylindrical grin lens as an example, and that's the example that we're using throughout the series. And we wanted to address a question that, I think all antenna engineers should ask right away when considering a different type of antenna structure is, is that type of antenna structure going to give me it's going to help me meet my RF performance requirements better? Is it going to help me meet those objectives? Is it more efficient in any particular way than an alternative? And so we set about to sort of perform a competition, if you will. So a traditional lens structure might be a zone plate lens. So if you look up Fresnel zone plate lenses, they're a classic structure that use staircase shaping of solid dielectric to perform that lensing function. And they tend to be reduced in volume and weight as compared to a traditional optical lens. So there's already some precedent for depending on your RF performance requirements for choosing a zone plate lens over a traditional, say spherical lens or something like that. And so the question is, does the Grin lens, with its added design freedom, give us a further advantage over what could be done with a zone plate lens? And, a Grin lens is typically using a fixed shape to start with, and then we're varying the dielectric to provide the focus. We could also sort of combine both ideas and use a variable shape with varying dielectric, but that's even more flexibility in the design process, more design variables. So for now, let's just focus on varying the dielectric. So our question is, if we're going to use the same working volume, is there a performance or other benefit to using a Grin lens versus a zone plate lens? So our case study is a 16 gigahertz patch antenna that is illuminating the lens volume. Each of the lenses are designed to use the same focal distance and to occupy the same volume. Thus, the full assembly occupies the same volume, and we feel like this gives you sort of the best comparison, apples to apples. And we want to look at, typical antenna parameters like return loss, peak gain, gain patterns, etc. So we're going to go into a lot more detail in the third webinar about the design process for both of these lenses. So right now I'm just giving a very quick overview of how both of the lenses were designed and some initial simulation measurement results. So on the design side, these are fairly simple lenses that actually have an analytic starting point for the design. So if we assume a fixed total thickness of both lenses and a desired focal length, both lenses are assumed to be printed using Rogers Radix 2.8, which Phil described earlier. And we know we want to print these on Fortify's printers, and there is some manufacturing guidance about the choices of available permittivity ranges given a choice of material like the Radix 2.8. So we're taking that into consideration and allowing for the accessible ranges of lattice structures that yield effective media properties that are favorable for these lens designs. So the focal length for both lenses is 35 millimeters. So it's just a smidge under 28 millimeters thick. And you can see sort of typical design equations for either a zone plate lens or the cylindrical Grin lens. And if we just hop to sort of the end of the story, if you will, we first started by performing a simulation of just the patch antenna by itself. Got some baseline data for that. So we know the patch antenna, as we can see here on this middle polar plot, the patch antenna gain is about 7 dB, fairly typical for a patch antenna. And when we add in the zone plate lens or the Grin lens, because of the spacing between the patch and the lenses, the return loss isn't really affected. And we see these little cluster of 3 curves here. That's the patch plus the zone plate lens, and the patch plus the Grin lens. So that's as expected. That's desirable. And jumping ahead, hinting to some of what we'll see in the third webinar, we see measured data here, and once again, the patch, zone plate lens, and Grin lens all agree very well with each other and line up as expected. And with both lenses, we get a gain enhancement. That's the goal after all. It's about a 14 dB gain enhancement. So if you were to compare the size and the aperture size and the typical depth of a standard gain horn operating at 16 gigahertz and this patch fed, either one of the patch fed lenses, you'd see that the patch fed lenses are giving you a much more compact and lighter weight physical structure for the same gain performance. But then we have our question of, is the Grin lens, offering any benefits? And even though they occupy the same volume, have the same aperture area, the Grin lens does actually give about 1 dB more of bore sight gain, but notably it reduces the back lobe by about 10 dB, which could have some pretty serious performance effects depending on your application. So right out of the gate, we see at least 2 advantages from an RF standpoint of using the Grin lens over the zone plate lens. Both provide a really nice gain enhancement, and lensing structures in general are providing an enhancement over a typical alternative antenna structure. So overall, very, very nice result. And as we go through webinar 2 and webinar 3, we'll talk in a lot more detail about how these were fabricated, how they were designed, manufactured, and tested. And so that concludes my section. So I think we'll open it up for some Q&A, and I'll leave this slide up on the screen while we talk through the Q&A. So jot these dates down for the part 2 and part 3 of the webinar series. So Jessica, any questions from the audience?
We have some questions, and then everybody else who's still on, feel free to keep adding them, but I'll start reading some of them off. Okay, the first one is, how long did the prints take for the zone plate and the Grin lens? Is there an estimate?
Yeah, I can answer that question. Yeah, we printed those lenses on our printers at the Fortify lab in Boston. Interestingly, they occupy the same Z height, which is, can't remember the exact Z height, Daniel. I think probably like 30 millimeters. Is that right?
Yeah, about 28 millimeters.
28. So both parts, both builds ran about 6 hours. So build time is about the same between the two, because our printing process is primarily determined by how high we are building on the build, and due to the orientation being the same between the 2 lenses and the 2 builds, they both took about the same amount of time. That was about 6 hours, and each build had 2 lenses on it. So that meant that we're about, from a unit count, about 3 hours per lens of printing time.
Okay, thank you. We have another question. In upcoming webinars, are you going to cover the lattice design in more detail?
That's right, yeah. So we just had a short period of time today to do the introduction of some of this technology, but we have quite a bit more content we're excited to show to our audience members in the second webinar, which is June 25th. As you can see on the screen here, I'll be going into a little bit more detail about the gyroid unit cell, which is the unit cell that we commonly use at Fortify for our latticing, Grin latticing technology. And also talk about some of the details that we understand about that relative to dielectric ranges at certain frequencies, and what you can expect from a performance standpoint based off of those considerations. So yeah, we'll definitely be sure to cover that for sure.
Okay, and then just as a reminder, feel free to put questions into the chat or into the Q&A, and I can read them off. And then here's another question. Phil, since it's likely that these lenses are likely to be heated near other electronics, how robust is the lens performance in response to thermal expansion?
Yes, so there's a couple ways to think about that. One, when we think about the thermal characteristics of a lens, you have to consider the thermal environment, not just from the nearby electronics, but also, what ambient environment are you going to be exposed to, and then the considerations therein. If we look at the ceramic material, if we take that as an example, we have a performance, a temperature performance that we expect to range up to about 1400 C without significant changes to the behavior of the material. We're still working to verify that, but in the ceramic material, we would expect very limited impact of any thermal expansion. The if we were to think about the polymers, we can make available, and it's available on our website, the material technical specification for the radix materials, and it does have an HDT of around 76, and for the lower of the two pressure cases. But we've been doing some extended thermal analysis with our partners at Rogers that suggests that the long-term exposure of about 125 C shouldn't impact the dielectric performance of the materials. Now, when you think about lenses, it's the combination of the material and the geometry that impacts how the material forms. So long as we're staying below the HDT and the part's not under any load, we wouldn't expect any impact the focusing characteristics of the lens from a mechanical standpoint. I'll be sure to introduce a little bit more of this type of data in the following webinar, so that if you're looking for a little bit more comprehensive information there, I can provide it there.
And then a follow-up to that, someone asked a question, are the materials space qualified?
So we're working towards space qualification. None of them are currently space qualified. The materials have gone through the NASA outgassing, which they do pass. The 2.8 DK Rogers radix material has passed NASA outgassing. But the materials are not yet space qualified, and we expect to get our first parts in the space within the next year or two.
Okay, thank you. And then we have another question. Why does the Gren lens have a lower back lobe than the zone plate lens?
Jen, you want to take that one?
Yeah. So if you think about the zone plate lens, at its base, it's solid dielectric. So the full diameter of the lens, the base, first section of it is just solid plastic. Or solid material there. So when you think of the wave coming out of the patch antenna impacting that solid boundary versus this impedance tapered boundary of the Gren lens, you could think of it as it's a harsher change, and therefore a greater impedance mismatch, and therefore signal is bouncing off and going backwards. Whereas with the Gren lens, there's better impedance matching, so the wave soaks into the lens, if you will, more easily, thereby reducing the back lobe.
Great, thank you. And then we have another question about future webinars. Will we address the bandwidth of both lenses, lens designs, and true time delays in any of the future webinars?
Yes, the bandwidth of the lenses themselves are inherently broadband structures, and in this particular example, the factor limiting the bandwidth is really the feeding patch antenna, but we will talk more about bandwidth impacts associated with the lens design in both of the webinars.
Okay, and then we have one other question. If Phil could expand on what he meant when he called the DK effective.
Yeah, of course. So when we are thinking about the dielectric constant of a material, just a solid bulk material, we have that dielectric constant, and that's all there is. But when we are locally mixing air in through geometry, as we're doing with our latticing, we create we call it a metamaterial, you can call it effective media, you can call it a number of things. We refer to it as the effective dielectric constant. And that means that based off of that criteria of volume fraction of air to dielectric within a region, and you were to measure that, that would be the effective dielectric constant of that small region. We've done a bunch of characterization of this through waveguide, through free space test methods, and in physical part measurement to validate our approaches. But yeah, effectively, what we mean when we say effective dielectric constant or effective DK refers to the ability to tune the dielectric constant of a specific region by using that approach, that latticing approach. You're welcome.
Okay, and I think that's all of our questions. Thank you, Dan and Phil, and thank you everyone for attending the webinar, and we hope to see you in the next installment. Thank you. Have a great day.
Thanks, everybody.